Hi everyone. In our previous video, we defined a concept called group. We call that a set G closed under a binary operation is a group if and only if 1. The binary operation is associative, 2. There exists a unique identity element for the binary operation in the set G, and 3. Corresponding to each element X in G, there is an element Y in G as well, such that when we operate them, xy equal to yx equals the identity found in 2. Now we want to introduce a special type of group called the Abelian group. We define this formally using 4.3 definition. In 4.3 definition, we define Abelian group as a group G. It has to be a group G and is abelian if its binary operation is commutative. Here we can see that whenever we define a group as in 4.1 definition, or whenever we have a given group, we can always further categorize them into whether they are abelian or non-abelian. We simply check whether the binary operation is commutative. Now let us look into some examples. In 4.4 example, let us have a set of positive integers z plus. We know that the main ingredient for a group is a set. Here we have the set of z plus. And second one, a closed binary operation. So we need to define an operation too. Let's say we consider this set of positive integer under addition. We want to check if this forms a group. Here we quickly see that it is not a group. Why? Yes, because we know that 0 is the identity for addition and 0 is not included in a positive integer set. This violates the axiom 2 of our very definition for a group. Therefore, we can give a reason for this as there is no identity element for addition in the positive integer set. This reason is sufficient, although if we want to be more precise, like saying there is no identity element 0 for addition in the positive integer set is also acceptable. If we include the additive identity 0 into a positive integer set in 4.4 example, we can form a set of non-negative integers. We examine this in 4.5 example. Now we already passed axiom 2. However, it is still not a group under addition because there is no inverse for some of the elements. There is an identity 0, but there is no inverse for some of the elements. Here, we might give any possible counterexample, say 3, that has no additive identity in this set. We know this by heart that negative or minus of 3 is the additive inverse for 3. In 4.8 example, we consider the set of positive real numbers R plus and the non-zero real numbers R star, each under the binary operation of the usual multiplication. Both of these are groups. We can check that these two satisfy the conditions of the set becoming a group. Just for a point of note, although we have 3 axioms in the definition 4.1, students must also check that the definition starts with the term closed under a binary operation. Thus, it is a very good practice that before checking for the 3 axioms, students should check first whether the binary operation is closed. Here we can see that for both, multiplication is closed. This means that multiplication of positive reals will always give you a positive real, never 0 and never negative. And likewise, multiplication of non-zero real will always give us non-zero real, never the case that we will get a 0. Then we check for each of the axioms. Under axiom 1, we can simply conclude that the usual multiplication is always associative. While for axiom 2, we have the multiplicative identity 1 for multiplication in both sets of positive real and non-zero real number. For axiom 3, we know that for each positive real number A, we will have an inverse of 1 over a, which is again in the positive real number set, such that a multiply 1 over a gives us 1, the multiplicative identity. The same reasons hold axiom 3 for the set of non-zero real numbers R star. And the same reasons hold axiom 3 for the set of non-zero real numbers R star. Now, because we know that usual multiplication is always commutative, thus we say that these two are abelian groups. However, the set of real numbers R under multiplication is not a group. Why? For this, I want each of you to comment below with your reason of why this is the case. Additional examples are also provided in our main text. Please read them through to get a deeper idea about this concept. Now, let us do a practice. This is a question. Let n be a positive integer and let n of integer equal to the set of n multiply m, such that m in integer set. Okay, so it means that you have a positive integer n and multiply with m, any integer. Okay, show that n of integer is a group under addition, the usual addition. Now let us pause this video and practice ourselves. You can resume back this video after you finish writing your answers, and we will discuss the suggested solution. Okay, good job for doing the practice. Now let us look at the solution. First, we check for the closure of the binary operation, the addition, on the set nz, n of the integer. So we choose any two free elements from the set of nz. Say we have nr and ns. To check the closure of the binary operation on the set, we need to show that nr plus ns is also again in nz. We have nr plus ns equals to n of r plus s. Now we see that the result is n multiplied with the sum of r and s. Since r plus s is always an integer and n remains as a positive integer, we conclude that this is in fact in the set of nz. So we conclude that nz is closed under addition. Then we check for axiom 1, the associative of the binary operation. Now it is easy because we know that the usual addition is always associative. Thus, we move to axiom 2, the identity for addition. We already know that 0 is the additive identity. However, for this problem, it is a little bit tricky that we need to show that the identity 0 exists, or in fact, in the set of nz. Since 0 equals to n multiplied 0, we see here n is the positive integer as needed, and 0 is an integer. Thus, 0 satisfies the characteristic of becoming a member of n of integer. Thus, we can say that this identity 0 exists in nz, and axiom 2 holds. Finally, we check for axiom 3. Here, we need to show that for each element nm in nz, we must have another element again in nz, such that when we add it with nm gives us the identity n0 equal to 0. So now for each element nm in nz, we also have n of minus of m in nz. Here we see that n is the positive integer and minus m is an integer. satisfying the condition for becoming a member of NZ. Adding this to NM, we have NM plus N of minus M equals to N of M minus M. And this equals to 0, the identity that we stated in axiom 2. Thus, for any NM in NZ, we have a unique inverse for them, namely N of minus M in NZ. Okay, we see here that N is the positive integer N here, and minus M here is the condition for M, which came from integer Z. Consequently, we have shown that NZ satisfy group conditions under addition. Therefore, NZ is a group under addition. Now let me ask you, is this group abelian? This is the second question for this video, and I want each of you to reply with your answers in the comments below.